Hello, welcome back to statistics. We're talking about analysis of variance. We're going to talk about the basics here. So this lesson and the next several lessons will be going through the components of the calculations one little piece at a time. So the first piece is called the grand mean. It's the easiest piece to understand. It's very, very simple. But before we get to that, let's look at this problem. What we're going to do is end up solving this problem by hand. I know in the previous section we talked about school districts and testing. That was great to keep in your brain just because everybody has some experience with grades. But this is a real problem. So below are the ages that females get married in New York, Texas, and Oregon. So you see we have New York here, Texas, and Oregon, and we have some numbers written down here. So these are the ages that girls get married. So in New York, we have one person that got married at 18 years old, and one at 19 years old, and so on. So everybody you ask, there's 10 people that we sampled in New York, 10 people we sampled in Texas, and 10 people that we sampled in Oregon. So this is another example. The population that we're studying is the entire New York female population, the age that they get married. The population here is all the females in Texas. The population here is all the females in Oregon, but we can't sample everybody. What we want to do, but we just can't do that because there's not enough money or time. What we want to do is perform an analysis of variance test to see if the average age of marriage in these three states are equal. So again, analysis of variance, 3 or more populations, in this case 3, but we could have Louisiana and Kentucky and Florida if we wanted to. We could continue doing testing and do them all at once. But we cannot know the population average. We can't sample all girls in Texas, all females, and figure that out. It's just too costly. So we sample 10 from each of these guys, and we want to figure out from that information at a 0.1 level of significance, which means 90% level of confidence if this data indicates that the average age of marriage in these three states are the same or not. Now I have the numbers here because the equations I'm going to write down are going to have subscripts 1, 2, 3. So when you see a number 1, it means New York, number 2 means Texas, number 3 means Oregon. You should label your data that way as well. All right, so first thing we need to do is write down the null and alternate hypothesis. And I already told you that it's always the same for these problems, but let's write it down anyway. The null hypothesis is that the average age that females get married in New York, see mu number 1, this is population 1, is equal to the average age of the females in population 2, which is equal to the average age in population 3. That's the null. That's the currently accepted hypothesis that we think is true. What would then be the alternate hypothesis? Well, it just means that at least one of these means is different. And I want to remind you, we did talk about it in the last section, I want to remind you though that even at the end of this test, I'm really not going to know which of these means is different, if any of them are different. I'm just going to know that one of them is different. You have to do different testing beyond the scope of ANOVA to figure out which one of them is different. All right, so the first thing we're going to talk about is the concept of the grand mean. So let me write that down. Grand mean. Because here's the deal. I've got sample data from population 1, sample data from population 2, sample data from population 3. So what I'm going to end up doing is I'm going to average this data and I'm going to get a number. That's going to be the sample mean from population 1. Then I'll average all of this and get a sample mean from population 2. Then I'll average all of that and I'll get a sample mean from population 3. So I'll be comparing those 3 sample means together. I'll be comparing them. But how am I really going to know if any of them are different? I mean, what were you doing in the previous section where we're looking at the test scores? I mean, I graphed it so you could visually see it, but what were you really doing? You were looking at those 3 scores and comparing them to each other, but really what you were doing is comparing them to a common baseline. The common baseline that you're going to end up using to compare each of these averages to is what we call the grand mean. Basically, you have all of this data here, so if you take the mean of each of these sample means, let's say you get a sample mean from this data, sample mean from this data, sample mean from this data, so you have a mean from New York, a mean from Texas, and a mean from Oregon. If you average all 3 of those means together, you get what we call the grand mean. So I'm going to write it down. It is the mean of the sample means. right? So I'm going to say this a few different ways. It's a really simple concept, but the reason I'm saying it this way is because your book is going to describe to you. It's going to say the grand mean is the mean of the sample means. And a lot of people look at that and say, what does that mean? Well, I'm telling you what it means. You average up your data here, you get an average. We call it a sample mean. Average this together, we get another sample mean. Average this together, get another sample mean. But we need a common baseline to compare everything to. So we take all of these three means and average them together. That's why we say it's the mean of the sample means. Now, when you mathematically do that, when you take this and average it with this and average it with this other sample mean, what you're really doing, is just averaging all of the data together. That's really what the grand mean is. So some books make it really difficult to understand that concept, but basically to calculate this grand mean, all you do is you add all the numbers together. You end up adding them all together, and you divide by the total number of samples you have across everything. That's the grand mean. It's exactly the same answer as if you take the individual sample means that you calculate and average them together. So either way you want to think about it, you're going to get the same number, right? Now I'm telling you this in words because now I'm going to write the equation down, and the equations scare a lot of people. So just bear with me. I'm writing them down so that you can learn how to read them. So the grand mean is denoted like this: X double bar. Not a single bar. Notice the sample means have a single bar, right? Because when you think about it, this guy is going to give you a sample mean, X bar 1. This guy is going to give you a sample mean, X bar from population 2. This is going to give you X bar population 3. Single bar means sample means from each individual population. Grand mean, double bar, is the grand mean. It's the mean of everything. So let me write the equation down. It looks ugly, but it's not that hard. So here you have a sigma. I'll explain all this in a second. I is equal to 1 up to k. Open up a bracket, and we have another sigma here inside this bracket. Looks really complicated. Don't worry about it. It's not complicated. J is equal to 1 up to n sub I over x I comma j. And I'll close this guy out. And now you're taking all that stuff and you're dividing it by another sigma, if that wasn't already enough, n sub I. Okay, the reason I took a minute to write down the grand mean and explain what it is in words is because if I give you this first, most people just fall asleep. And they say, this is difficult, I can't understand it, I'm not a math person. But it's really simple to understand. I already told you the grand mean is just the average of all this data, all of it, right? This equation is the way that you mathematically write that down. So I'm going to go through it because even though I could skip over it, what's going to happen is we're going to come across more and more of these things, more and more of these equations in the next sections. You need to learn how to read these things, because if you deny yourself that, then you're just not going to understand ANOVA ever. So just stick with me for a second. All right, first of all, I need to explain a few things from algebra, right? So this sigma here, this big E, this means you're adding things up. This one means you're adding things up, and this one means you're adding things up. Now I have to write a few things down off to the side before you'll really understand what it's saying. K, this value of K, is the number of populations. In this case, 3. Right, so there's 3 populations. So when I actually calculate it, it's going to be I goes from 1 up to 3. If I had 16 populations, then I would be going from 1 up to 16. All right. Then you have this guy here, and this guy n sub I appears in 2 different places down here. So I'll write this down. N sub I is the sample size of ith population. Right? So we have a population of New York. We took 10 samples. The sample size here was 10. Texas, we took the same number, 10 samples, so the sample size was 10. Here we took 10 samples, the sample size was 10. So I is just a letter that represents a number. So the way what I'm really trying to get across to you is n sub 1 was 10 because we took 10 samples. N sub 2 was 10 because we took 10 samples. N sub 3 is 10 because we took 10 samples. But again, when we do ANOVA, I'm doing it with the same number of samples now, but you know, I could take 7 samples from New York, 8 samples from Texas, 10 samples from Oregon. N sub 1, N sub 2, and N sub 3, the sample sizes would just be different. All right? So now it's time to try to figure out what this is really telling us, okay? We have an outer and an inner, right? So what we do is we work out to n first. I goes from 1 up to k, which is three populations. So let's say I starts out being 1. So the value of I is 1. So that means we go in here and we put a 1 everywhere where the I is. So forget about the bottom for now. On the top, what are you adding together, right? J, which is another variable, starts from 1 and it goes up to n sub I, which means it's just sampling over the 10 samples from population 1, because remember, I is 1 to start out with. I starts out being 1, so we just let the second variable, J, go from 1 up to the total number of samples from population number 1. And this sigma means I'm adding together what's inside here is all the different values. Basically, all you're doing is this is telling you that you're just going to add up all the values from population number 1. Because, and I didn't write this down yet, I'll write it down right here, xij is the jth sample from the ith population. So as an example, I'm just going to give you a couple of examples. Okay, x11 from population 1, sample number 1, population 1, sample number 1 is just 18. Okay, x21, the first letter here is the population that you're on. This is the sample from the second population, sample number 1 is, second population is here, sample number 1 is also 18. And just one more example, x31, from the third population, sample number 1 is 21. So now you have all the pieces in place. Basically what's going on here is you start out with the outer loop, you set I equal to 1, and then you come in and put I equal to 1 here and I equal to 1 here. So you're summing, you're adding up, that's what the sigma means, you're adding up all of the values from population number 1 across J, which is the samples from population number 1. So I11, I12, I13, I14, I15, I16, I17, I18, I19, I10. So you're adding all those together. That's what the sigma means, right? Once you're done, you've gone up from 1 up to the complete, sample size that you had for that population. Then what happens? You pop out and you increment I. You go to the second population. So now I is 2. So 2 is here. So now you're adding up from here, going J from 1 up to the sample size of population 2 means you're going to add up all of these guys. X21, X22, X23, X24, X25, 26, 27, 28, 29, 210. You're just adding up all those values because you're going from this value up to the sample size of population 2, and then you do the same thing when you increment I to population 3. I31, I32, I33, 34, 35, 36, 37, 38, 39, 3, 10. So you see what you're doing. This entire ugly mess up here just means that I've added up all of these, plus all of these, plus all of these, which is what I told you the grand mean was going to do. It was going to add up everything, but then you have to divide by something, right? Notice what's on the bottom. You don't have anything on the top and the bottom. It means you just sum all of the total number, the sample size of the ith population. So population number 1 has 10 samples, population 2 has 10 samples, population 3 has 10 samples. You're not summing up the values in there, you're just summing up how many there are. So 10 plus 10 plus 10 is 30. So you see what's going on here? The top here is you're adding up all of these things, then all of these things to that, and then all of these things to that. You add all of them up and you divide by the total number of samples that you have across all the populations. That's what we call the grand mean. I could have skipped that. I know I spent some time on it, but I wanted you to understand it because you're going to see this kind of notation here. That's why I say it's the jth sample from the ith population. So population 1, then increment 1, 2, 3, 4, 5, 6, 7, add all of those up. Go to the next population, population 2, increment 2, 1, 2, 3, 2, 3, 2, 4, 2, 5, and so on. And then population 3, add everything up, divide by the total number. So now that you have all of that down, we're going to actually do it. Let's go ahead and calculate that for this data that we have. So I've stripped away the problem statement and I've left just the raw data here, essentially. All right, another way to write that, I know you're probably sick of math, but the grand mean, the way I wrote it before was very compact. This is another way to write it that's exactly the same thing. If I blow it out for this particular problem, I'm going to sum J is equal to 1 up to 10, x1j. So across population 1, I just increment the elements there. Let me get it all down here and I'll explain. J is equal to 1 up to the sample size of population 2, x2 j, and then I'm going to add to that j is equal to 1 up to 10 of x3j. All that's happening on the top is this is adding up all the elements from this population, this is adding up all the elements from this population, this is adding up all the elements from this population, because in each case I'm running up from 1 up to the sample size, 3, 1, 3, 2, 3, 3, 3, 4, so on, 2, 1, 2, 2, 2, 3, 2, 4, so on, 1, 1, 1, 2, 1, 3, 1, 4, so on. Adding them all up on the bottom, you know, we already said that it was the sum of the total number of samples that you have. So really on the bottom it's just going to be 10 plus 10 plus 10, which of course you know is the 30. So you're basically summing up all the samples divided by the total number of samples. That's what the grand mean is. So to be absolutely clear, the grand mean is, drum roll please, 18 plus 19 plus 20 plus 21 plus 22 plus 23, plus 18, plus 19, plus 20, plus 21. Okay, all of that is what this is doing. It's just adding up all of those elements, but to that, I have a second summation right after it, which is 18 plus 19, plus 20, plus 16, plus 20, plus 21, plus 20, plus 18, plus 19, plus 17, plus 13. Okay, and then I add to that from the last part, 21, plus 22, plus 17, plus 18, plus 22, plus 19, plus 21, plus 20, plus 18, plus 23. So I add all that stuff up, and I divide by 30. Now, I agree, I wrote a lot of stuff out there. I probably didn't have to write all that, but there's a reason why I'm writing it all out there. So what you're going to end up getting there, I think I do have enough room on this page, is x double bar is going to be 584. That's what you get on the top, divided by 30. So let's go ahead and write it over here with a little bit more room. X double bar, the grand mean in this case is 19.4. 66667. How many decimals you choose to carry is up to you. I'm carrying a lot because I want to make sure that I don't have any rounding errors as I go through here. So this is the grand mean. I'll circle it in red. And ultimately, I could have probably skipped about 90% of this whole lesson, because ultimately the grand mean is just simply the average of all of this data together. I could have just told you to do that. But I want you to understand where the equation comes from and how to read them, because we're going to be doing other equations for other calculations, and you need to kind of get used to seeing summation symbols. But ultimately, that's what this one was doing. This guy, 19.466667, is basically a representative average of the average age of marriage of females across all three of these states. So later on, when we calculate the sample mean of each guy separately, and we're going to have to compare it to a baseline. This is going to be the baseline we're going to compare them to figure out if any of them are deviating or varying with respect to any of the other guys. So we're going to be comparing them to this grand mean, essentially, is what we're going to be doing. So make sure you understand this. We're going to be calculating different parts of this problem as we go through it. We're going to be getting these sample means, comparing them to the grand mean that we just calculated, and then performing the rest of the ANOVA testing. This was actually the easiest part to understand. There are some other parts that are a little more difficult to understand, so I'm going to try to break it out slowly for you, make sure you understand it. I wrote all those numbers down just so there's no confusion about how I'm calculating it by hand. Then when you start using Excel, you'll know exactly what it's doing. There won't be no question marks for you. So make sure you understand this, follow me on to the next lesson, and we'll take apart ANOVA to the next calculation, to the next part of the puzzle to make sure you understand how to do it.